Good afternoon. Well, this is my poster. I'm going to talk to you about the design of scaffolds for bone tissue applications. These scaffolds are composed by polylactic, polycaprolactone, and hydroxyapatite. Well, thank you for listening. And well, I must say that in the last years, the defects in bone tissue have been more and more common in the society. This is why the biomaterials research has dedicated a specific area for the development and evaluation of materials that can offer this issue. The biomaterials must have specific requirements for working effectively in the recovery of damaged tissues, as the biodegradability, non-toxicity, and adequate mechanical resistance. In this investigation, the research led to develop scaffolds with hydroxyapatite, which is organically present in bones and teeth, polylactic acid derived from lactic acid, and commercial polycaprolactone. The hydroxyapatite was synthesized by the wet chemical precipitation method, while semicrystalline polylactic acid was obtained by a monomer ring opening polymerization. The synthesis modification has been not described before and present the advantages of not using the Schlenk line or a vacuum chamber to remove the humidity of the synthesis. Which one is this modification? Well, we use a helium atmosphere. Posteriorly, by solvent casting fat leaching technique, the compositions of scaffolds were developed. Two different compositions, hydroxyapatite 10, polylactic 10, and polycaprolactone 80, and hydroxyapatite 30, polylactic acid 10, and polycaprolactone 60. As seen at the poster, the equipment for the polylactic synthesis is very simple. Well, it's also economic, and the polylactic acid obtained is of high quality, as we can observe in the XRD evaluations, and also in the FTIR pattern. For an orthorhombic semicrystalline polylactic acid, which was the species that was synthesized. A remarkable issue for this synthesis is the melting temperature of the PLA species that was analyzed by thermogravimetric analysis and differential scanning calorimetry. This melting temperature was read at 332 Celsius degrees, which is higher for the presented in the commercial polylactic acid. This is about 150 Celsius degrees. The hydroxyapatite was also obtained with high purity. Posteriorly, the composite scaffolds obtained were evaluated to observe its morphology, which is heterogeneous as expected, but well dispersed as observed in the same images. The mechanical test was taken under compression conditions, and well, the mechanical test was done to compare the values to cortical or cancellous bone. Cancellous bone plays an important role as a primary load-carrying component that absorbs energy. This bone is an anisotropic and porous composite, and its mechanical properties depend not only on the porosity, but also in the arrangement of each trabecula, and it has a modulus between 0.5 gigapascals. For analyzing the compression properties of the developed materials, the evaluated samples were cylindric porous 3D scaffolds, as we can observe in the poster, with a size relationship leg diameter of 2 to 1. It is loaded at constant force, and the data of shortening is collected through a force transducer. The mechanical behavior was nearly up to the 70% of deformation for both compositions, indicating that the material presents an elastic response of the structure. The scaffold formed by a major quantity of hydroxyapatite presents a maximum compression of 3 megapascals. The overall results confirm their usage in biomedical areas, specifically in bone tissue applications. There are some work to do next. as the evaluation of cytotoxicity and the observation of the composite degradation under physiological fluids, among others. At last, I want to thank your attention and to do extensive my gratitude to the Universidad Michoacana de San Nicolás Hidalgo and to the Mechanical Engineering faculty and also CONACYT for all the support given. Thanks again and warm regards.